Hello and welcome dear friends. So in continuation of the last class, today we will discuss about the violation of assumption. So what we mean by the violation of assumptions, basically in this specific lecture we will talk about the violation of the assumption of homoscedasticity and violation of the assumption of no multicollinearity. So what is the concern of the violation of assumptions? So once we estimate the parameters, that is once we get the value of, let us say, this beta 0 hat plus beta 1 hat x1 plus u hat. So once we get the value of this beta 0 hat and the beta 1 hat, that is the estimates we get. The next question we have to answer is how reliable these estimates are. Because once we make sure these estimates are reliable, then only we can make the inference about this. To test the reliability or to check the reliability of these two estimates, we depends on three criteria. So what is known as the a priority criteria, statistical criteria, and econometric criteria, what are the second order test. A priority criteria where basically we used economic theory to find out the reliability of these estimates. How we do that? So let us take an example here. So what we know that the consumption, if we estimate, let us say this beta 0 hat plus beta 1 hat income. So this is the consumption function we have. Now once we get the estimates of this beta 0 hat and beta 1 hat, using the economic theory, we can make sure whether these estimates are reliable or not. From the economic theory, what we know, this beta 1 hat basically is nothing but the marginal propensity to consume. And from economic theory, we know the marginal propensity to consume will lie between 0 to 1. What is marginal propensity to consume? It says that if your income increases by 1 rupee, how much of that increased income you will consume. So that is the marginal propensity. And from economic theory, we know it will be more than 0 and less than 1. Now let us say if we have this beta 1 hat, let us say it is 1.2. But economic theory says that it must be less than 1. That means this estimate is not reliable. So this a priori criteria, through which basically we see the size and sign of the estimate, and using those two criteria, we can see whether the estimates are reliable or not. The second criteria we use, the statistical criteria defined by the statistical theory. For example, we use the standard error to test the significance of the parameters, or we use the t-statistics to test the significance of the parameters. Then the third criteria, what we know, the econometric criteria, which is known as the second order test, which is defined by the econometric theory. So why we have the second order test criteria? So basically, if you recall that these statistical tests are valid only if the OLS assumptions are satisfied, because the statistical properties of these estimates depends on the assumptions of the OLS. So we have assumed that we are deriving OLS assuming that those assumptions are satisfied. If those assumptions are not satisfied, then the property of these beta 0 hat and beta 1 hat, for example, the variance, the mean, may not be optimal. So in that case, the statistical theory may not be able to satisfy. So this violation of assumptions, basically, if that is the violation of assumptions, that means estimates may not have the optimal property. Therefore, this econometric criteria assesses the goodness of the estimates based on the validity of the violation of assumptions of linear regression. So before discussing the violation, let's quickly discuss the assumptions, though it has been discussed into the two variable regression model earlier also. So the first identification data description, there must be the variation in x. If there is no variation in x, that means we will not be able to identify x1 how it is different than the x2. So there must be variation in x to identification data description. Similarly, for the unbiasedness and consistency of OLS estimates, it must satisfy variation in x, random sampling, linearity in the parameters, zero conditional mean. Similarly, if it is has the Gauss Markov theorem, that is if it is blue based linear unbiased estimate, then it must satisfy, in addition to the zero conditional mean, it must satisfy the homoscedasticity. Similarly, for the classical linear regression model, including this, in addition, it must satisfy the normality of errors. More than that, we have also assumed the no autocorrelation. So basically, in this, when we talk about the violation of assumptions, we will talk about the assumption of homoscedasticity, assumption of no autocorrelation, assumption of no multicollinearity, and assumption of no specification error. So these four is the very critical assumptions we have, and we will talk about these. So when we say violation of assumptions, that means we have assumed that there is a homoscedasticity. If there is no homoscedasticity, that means there is the violation. We have assumed there is no autocorrelation. If there is the presence of autocorrelation, that means there is the violation of assumption. So basically we will discuss what will be the consequences of this, what are the situations when we will have such situation, and what are the basically way out of such situation. So let us first start with the homoscedasticity. So what is the homoscedasticity? The homoscedasticity is the assumption of the equal variance. That is, the error term has the equal variance. Mathematically, which we could write, the variance of ui is basically expectation of ui minus expectation of ui whole square, expectation of u square sigma square u. Here, since expectation of ui is equal to 0, therefore it turns out to be this. That means if we are telling the homoscedasticity, that means there is the equatorial stator from the mean value dispersion is similar we have. On the other hand, if the assumption of homoscedasticity does not hold, that means we have the problem of heteroscedasticity, that is unequal scatter. So in that case, the variance of ui will be summation of sigma square, and the ui, it will depend on the number of time periods or observations we have. Or saying the equivalently is, this means that the dispersion of the observed values of y around the regression line is the same across the all observations. So it basically says that if we have x here, y here, and we have the estimated regression line, the equality of the variance reflects that the dispersion of the observations around this estimated regression line is always same. To understand better this, let us see the certain graphs where we are basically drawing y on the y-axis and x on the x-axis. Now we can see here, this is the estimated regression line we have. Now what we can observe, as x increases, the value of y is also increasing, which is captured by this estimated regression line. And another thing what you can do, observe here, as the value of x increases, the value of here, that is captured by this estimated regression line, as well as here the value of x are also increasing, but the dispersions around this estimated regression line remains the same. On the other hand, it could be the another relationship here. So again, the relationship is estimated by this, where we can observe as the x increases, value of y is also increasing. However, one another thing we can observe, as the value of x increasing, the dispersion of the observations around the estimated line is increasing. Or we could have a situation here that where the dispersion was higher, then as x increases, the dispersion is decreasing. Or we could have another relationship where we can see the dispersion was more, as the value of x increasing, dispersion is decreasing, but again after a certain point, as the observation x is increasing, the dispersion is increasing. So that means What we can observe in case of the homoscedastic error, the variance of ui does not depend on the value of x, instead remains the same irrespective of values of x. However, in case of heteroscedasticity, what we are observing that as the value of x is changing, the variance of u is also changing. That means we could write a functional relationship between the variance of the ui and the values of x. And the pattern of heteroscedasticity depends on the sign and the values of this coefficient. As we have seen in the previous slide here, as x changes, variance could increase or variance could decrease or variance could increase and later again it could decrease or increase. So from this, what we can observe, the when we say that there is the heteroscedasticity, if there is the relationship between the variance of the error term and the regressor or independent variable. And if there is no relationship, we assume the homoscedasticity. Now, how much the feasibility of this assumption? So we are assuming that there is constant variance. How much it is possible, how much it is feasible in the real world. To understand that, let's first think why we include ui. We include ui in the regression equation to capture the error in the measurement of the dependent variable and include the effect of the omitted variables. So if there is the omitted variable, effect of this will be captured through error term, and if there is the error of measurement in the dependent variable, we could include that, capture that through the error term. Now, one is that as y increases, the measurement errors is also increasing. If let us say GDP, if it is smaller fraction is there, smaller GDP, then the error margin of error will be also smaller. However, if the GDP is increasing, or let us say the investment in the firm increasing, there is chance of measurement error is more and more. However, let us say if somehow we could control that, but let us take another case here, omitted variables. We have discussed that economic relationship is not so straight. There is the complex relationship we have. When we say complex, we mean that one variable is being affected by large number of variables. And in such cases, often we cannot include all the variables. And there could be the two reasons. One, in some time we may not have the observation of the certain variables to include the regression equation. We cannot measure the size. For example, behavior of the people, it's quite difficult to include that and to observe that or to have the quantitative value of those. If we do not have, that means we will not be able to include that into the regression equation. Second aspect, not able to include comes from the degree of concept of degree of freedom. So what we have degree of freedom, n minus k, where n is the sample observations, k is the number of parameters. This number of parameters will keep on increasing if you add the additional regressor. So if we number of parameters will be 2 included in the constant when with the regressor have x1. If we have the number of parameters will be 3 when we have x1 and x2. So on, as number of regressors, number of variables increases to capture and more factors, you will have more and more number of parameters. However, if the number of parameters increasing, then we will have less number of degree of freedom. If the less number of degree freedom we have, then we will have the problem with the estimates. The reliability of estimates will be less and less. Therefore, in real world scenario, in most of the times we will have the certain variables which may be the significant, but we will not be able to include into the regression equation. If that is the case, that means the assumption of heteroscedasticity, homoscedasticity will be satisfied is little bit doubtful we have. Let us take an example of saving and income relationship to better understand this situation here. So what basically we have this scenario here. So here we are assuming this is a 3D diagram. So where we have this FI functional relationship between Y and income, and on the y-axis we are measuring the saving, and x-axis we are measuring the income. Basically, it shows the relations between saving and income. So from this estimated line, regression line, what we are observing, as income increases here, the saving is also increasing. And another important observation we can get from here, that the dispersion of this at every income level is same. So what basically we mean here, let us say we have the income level is rupees 200, then some of the household may be 60, another household may be 40, another household may be 20. So the variation observation are this. So the maximum is minimum is 20 and maximum is 60. So let us say the range variation is 40. So here the assumption is that if the income increase the 400, so in the similar proportion it is increasing here, it will be 40 and it will be here 80. So the dispersion remains the same at every income level, though it captures the fact that as income increases, the saving is also increasing, but the dispersion also remains the same. However, if we observe the real world, the scenario is different. Why the scenario is different, let us think of this way. So as income increases, the saving is also increasing. However, what we can observe from this here, in case of the lower income, which is associated with the poor people, the saving follows this particular dispersion here. However, as income increases, which could be associated with the rich people here, there is the large variation into the saving behavior here. Why could be the large dispersion here? When the rich people, they have a custom with the higher consumption. If they have a custom with the higher consumption, if there is the decreased income, they may not decrease their consumption to save the same amount, rather than they can reduce their saving behavior. So there is a large variation among the rich people. However, in the poor people case, most often they try to save certain amount to make certain future decisions. So in that case, there will be less variation. So this is the example of the concept of homoscedasticity, of assumption of the homoscedasticity, whereas this is the example of heteroscedasticity. So often we can observe that in the real world, often we face the concept of heteroscedasticity rather than homoscedasticity. Now, if that is the case, let us say there is the heteroscedasticity, what are the consequences we will have? The first consequence is the OLS estimates will not be best or efficient. That is, the variance will not be minimum, but it is unbiased and the consistent. So this is not best, no more blue. If that is the case, we often use the generalized square instead of the OLS method. So in the generalized square, basically it gives more weight to the observations with the low values of xi, and vice versa we do. Another consequence what we have, f and the t statistics are likely to give the inaccurate results, statistically insignificant coefficient. Why will have? Because this confidence interval based on the variance will be unnecessarily large and standard error will be biased. So what one consequence is, no more blue properties of the OLS estimate. Second, we will have biased standard errors, and often we will have large variance and covariance we will have. Then what are the remedies we have? So when the variance is known, the method of the weighted least square or the generalized square we can use. When the variance is unknown, we can use the wide heteroscedasticity or the consistent variance standard error. So that's all about the assumption of homoscedasticity. Now the second important we have the concept of multicollinearity. So basically assumption is there is no multicollinearity. Now the violation means there is the presence of multicollinearity. So let us say what is the basically assumption of no perfect multicollinearity. Assumption of no perfect multicollinearity is there is no exact linear relationship among the explanatory variables. So let us consider this situation here. So what basically we have here, we know that there is the x2 is nothing but the twice of x1 we have. So the x1 x2 are said to be linearly dependent because x1 x2 are perfectly collinear. If that is the case, what we call there is the presence of problem of multicollinearity. Then what does it basically mean here? So let us take this equation. So we can write it y is equal to beta 0 plus beta 1 x1 plus beta 2. Now you can see here x2 is nothing but the twice of x1. So let us write here twice of x1 plus q2. Now we have y is equal to beta 0, beta 1 twice plus twice beta 2 and x1 plus u2. So basically these are the constants. So we can write y is equal to beta 0, beta 3, x1 plus here the error term. So in that case now we will have beta 3. Now going back from here it is not possible to go back here. So that's basically what we mean by the problem of multicollinearity. Now so there is the problem of multicollinearity. So that means what we can say, the existence of perfect or exact linear relationship among some or all experimental variables of a regression model is the problem of multicollinearity. If that is the case, the regression coefficient become indeterminate and their standard errors are infinite. We cannot estimate beta 1 and beta 2 separately. If there is the imperfect, the regression coefficient determinant but possess the large standard errors, which means the coefficient cannot be estimated with the great precision or the accuracy. However, it is the feature of the sample data rather than the population data. What does it mean? Because in the population, what we mean, there is the two relationship we have. The variance and covariance among the experimental variables are given. So there is no relation, there is no problem of multicollinearity because those relations do exist there. However, using the sample observation, we wanted to find out those true relationship. So while we are using the sample observations, though there is the chance we are taking those observations which may have this certain kind of problem. That's why we call that multicollinearity is the problem of the sample data rather than the population. Now, what are the sources we have? Why do we have the problem of multicollinearity? One, the data collection method is implied. If that is the case, for example, sampling over a limited range of the values taken by the regressors in the population. So due to the way we have collected the sample, so because of that we may have the relationship of this. For example, let us say if you wanted to find out the income, and to collect the data of income, we have went in such a household we have who happen to have the high level of education and high level of income. So here the relationship between income and education will be perfectly here. So by using the income we can predict the so that why we have, because we rather than taking the income of diverse people with the diverse education background, we have taken only those people who have the high educational background and the high income. Then constant on the model or in the population being sample. So that's basically, or the dummy variable trait. Dummy variable trait basically we say that let us say if we have the two categories. So let us say we have the gender. So we have the two category male and female, and to represent this we are taking dummy D1 and D2. In that case there will be the perfect collinearity problem, what we call the dummy variable trap. Model specification for adding polynomial terms to a regression model, especially when the range of the x is variable very small. That means if you are adding x1, then you are also adding the x square where you have very small number of observations. An overdetermined model, the model has more explanatory variables than the number of observations. There also will face the problem of multicollinearity. So these are the certain sources due to which we will face the problem of multicollinearity. Now, what is the consequences we have? The first, if there is the perfect multicollinearity, we cannot determine the parameters. So in the such case, parameters is indeterminate. we will not be able to estimate the parameter. However, if there is the imperfect multicollinearity, then estimates always may be imprecise. Why? Because the large standard errors. Affected coefficient may fail to attain the statistical significance due to the low t statistics. Sign reversal might exist, that is, the two relationship could be positive, but we may get the negative. The last addition or deletion of the few observations may result in substantial change in the estimated coefficient. So these are the certain consequences we will face in presence of multicollinearity. Now, how we detect that? So the one of the way is the high R square, but the few significant T statistics we have, that you should be doubtful about the presence of multicollinearity. Let us say we have the y is equal to here beta 0 hat plus beta 1 hat x1 plus beta 2 hat x2 plus beta 3 hat x3 plus u hat, where we have R square, let us say 0.98. However, the beta 2 hat and beta 3 hat is not statistically significant. That means there might be the presence of multicollinearity. So the individual coefficients are not significant, but overall significance is high. That means there might be chance of presence of multicollinearity. High pairwise correlation among the regression. So if we check the correlation matrix of x1, x2, x3 here. So if we have here, we'll have 1, here we'll have 1, here we'll have. So here let us say if we have 0.9 or here we have 0.82. So if we have the high correlation among the x1 and x2 here, and here x1 and x3, if we have high correlation, that there might be chance of presence of multicollinearity. The examination of partial correlations. So what in that case, basically what we do here, we find an auxiliary regression. So here let us say finding a R1, 2, 3, 4, that is basically finding of the correlation between these two, assuming 3 and 4 constant is very high, but the 1, 2 and 1, 3 is very comparatively low, may suggest that variables are intercorrelated and there might be presence of multicollinearity. Or we can use the concept of auxiliary regression. Basically what we do here, if we have, let us say, y is the function of, let us say, 3 variables or 4 variables, then what we do, we regress the equation x1 on the function of x2 and x3 and x4. Similarly, we regress x2 on x1, x3 and x4, and these are known as the auxiliary regression. In such cases, if we are getting high computing R square and this F is computed if it exceeds the critical Fi, there is the presence of multicollinearity. Then there is another concept, what we know, the tolerance and the variance inflation factor. We can use these two statistics also to detect if the variance of inflation factor is more than 10, that means there is the presence of multicollinearity. If the tolerance factor is close to 0, that again it means there is the presence of multicollinearity. Now, if let us say if we have used any of this method and we are able to detect there is the presence of multicollinearity, then what is the way out? What should we do? So there is the 2-3 approach we have. One, there is do nothing, just ignore. So there are the certain argument is there that you should not ignore the multicollinearity problem and don't do anything. Second aspect, we can do the combining the cross-sectional and the time series data, because the multicollinearity problem often we observe due to the cross-section, the time series, we have the two variables. So let us combine both this cross-sectional and time series data to avoid this. Or what we can do, we can drop one of the collinear variables. Let us say there is the multicollinearity between x1 and x2, there is the perfect. So either you drop the x1. So let us say if you have the two variables x1 and x2 and there is the high correlated we have, so either we can drop x2 or we can drop x1. However, if you do that, there might be result in the specification error or the specification bias. So it may create another problem. So you have to be careful while dropping the variables. Or The another is we can transform the variables. We can take the first difference rather than taking x1 and x2, or we can take the ratio transformation, x1 upon by x2 or x2 upon x2. So basically you are capturing the both the variables effect through the ratio. Or we can, because as we have discussed, this is the very simple related problem we have. So in that case, what we can do, we can add the new data to avoid that sample specific problem. Other methods for the remedy of the multicollinearity is the, for example, factor analysis. We can take the principal component method, or there is the regression. There are the many other methods are there to take the remedy. However, the prominent the methods for the remedy is that first, do nothing, just ignore it. Second, you add the new data. Third is often we use the principal component method to club those variables and take the one indicator of those variables. So that's in this class we have discussed the violation of the two assumptions, their consequences, how to detect, and what is the way out for this. Thank you so much. See you in the next class.